I'm Antonio Sala, and in this video we are going to illustrate via a simulation the behavior of the recursive Bayes formula, and we'll do that on the case study regarding a zookeeper that we are handling in a set of previous videos. Tiger was going left, right, randomly, and suddenly the gate closes, and then Tiger roars facing the door that would communicate the cage with the outside, or sometimes the tiger faces the passageway between left and right cages, so the roaring noise is heard at the wrong location. We have a conditional probability table in which, well, if we see the diagonal, basically most of the times roaring sounds are heard from the side the tiger is actually at. But well, there is a certain probability of listening to the wrong side, the off-diagonal elements. And if we summarized with this Q and R compact notation the conditional probabilities, then the posterior, the backward conditionals probability of cause-given effect can be computed with Bayes' formula, selecting the row associated to the here left or here right event, depending on what roaring event I did actually hear. So this was Bayes' formula with one row. And if we believed in conditional independence, so that successive roaring events were statistically independent from one another if the tiger did not switch side, because, the tiger moved a lot between roaring events or whatever, then we were able to multiply conditional probabilities and craft the conditional table for an arbitrary number of roaring events. For instance, in here, this would be the table of conditional probability, condition to tiger left or right, the 1 times 2 table. So this table is the one in which from a total of m plus n roars, m of them were from the left-hand side door and n of them were from the right-hand side door. So multiplying this times my prior belief b and this 1 minus b, I would obtain the joint, and the sum of them would be the marginal, and I would be able to apply the non-recursive Bayes formula. And in the video, which was the immediately previous to this one in the collection, we proved this result, saying that if I plug in the Bayes formula with the one row table as prior belief, the posterior from the past roaring events, then I was able to compute the posterior probability after listening to one more roaring event. So basically, applying the Bayes formula to the 20 roaring event non-recursive conditional table produced the same result than applying 20 times the single roaring conditional table in this recursive way. So we have a mathematical proof under, of course, conditional independence assumption, but now we are going to simulate that in order to understand the code and check that the numerical results of recursive and non-recursive evaluation indeed do coincide. So let us start discussing the simulation code. First 2 lines will just compile the application of Bayes' formula of the next belief if I hear left or the next belief if I hear right. In particular, the 2 lines I highlighted are numeric versions of these symbolic equations. So we have the next belief if here left, first expression, and next belief if here right. So once I have those functions, which are just functions of a single argument b, and they return b plus, the next belief posterior to the here left or here right event, then I will simulate, let's say that tiger is actually at the left side, and in this simulation tiger will not move, so it will be forever at the left side. That will be real tiger. I'll start with a non-informative prior, and then this is just cosmetic to tell my code how many roaring events I'm going to simulate and how many repetitions of that scenario I'm going to do. So I am going to do one simulation here, and I will listen to 8 roaring events, but my plots will have 9 elements because the first one will be the prior, but this is cosmetic. And then I will repeat for as many simulations as I wish, just one here, some flags and initialization condition for the plots, not important. The only conceptually important here is this, that I will start my belief estimation with the initial belief I did set to 0.5, and then first element in my list of results will be the prior, and then from second onwards it will be the posterior to the observations that, well, the first thing I'm going to simulate is just listening to left, left, right, left, right, left, right, left. So I have 5 left, 3 right, hearing noises, and we'll check that recursive and non-recursive evaluation yield the same result, of course. So I will be the index denoting each of the rows, well, I minus 1. So this fraction of code will not be used in my first simulation, is the one that will provide random observations. In this first simulation, I just tell that the observation will be the test observation I wish to simulate. But okay, let us analyze this fraction of the code because observations will be random in a minute. So in here, this is the conditional probability matrix, and as the real tiger is at the left side, then this PM here left, tiger left, is 0.8. So I'll throw a uniform random distribution, and if it is below 0.8, I will return an observation that is here left, and in 20% of the cases, I will return an observation that is here right. So with this, I am generating an observation according to the conditional probability table I had in my computations. Note that in real life, maybe tiger roarings do not closely follow my simplistic probabilistic model. So real life applications of statistics must take into account modeling error, but in here we are analyzing just a simplistic case. This is introductory material, so we will make our statistical simulation with no modeling error. So this is how we synthesize these random observations with the given probabilities, given in this case by the first column of this PM matrix. But in this first simulation, I just overwrite whatever we get here and just do the fixed observations in this test matrix. And then, well, the important code is this. Important but extremely simple. If I here left, then I apply Bayes' formula for here left, and if I here to the other side, then I apply Bayes' formula for here right. So I had a prior belief, and after applying Bayes' formula, I will have a posterior belief, and the recursive Bayes theorem proof will tell me that, okay, I can just overwrite that belief because this posterior will be used as prior in next iteration. That's recursive Bayes. So that's it. This is the core of my tiger state estimator. Because in real life, I would not need to generate the observation. I will just wait for them. They will come from my environment. And these last lines here are just cosmetic to put things in the plots and to flag when I am sure on where the tiger is, so my probability of being wrong is 1 over 5,000. Then I will flag that. But this is cosmetic. The important thing is this recursive Bayes filter and this way of generating my observations according to my probabilistic conditional model. So good. If I execute that, after listening to all the roars, my belief that tiger is right is just a little below 3 in 1,000. So I am fairly sure that tiger is left. Real tiger was left, and I am pretty sure that it's indeed left. With this plot, you can pause and analyze the code. It's just cosmetic. Here we have the evolution of the belief as observations are gathered. So kind of left observations diminish the confidence that tiger is right. Right hearing events increase the confidence it's right. And well, this sequence of observations ends up with this 2.8 in 1,000 belief that tiger is right. So 99 point something believe that tiger is left. And if we compare that, this 0.0028 with the evaluation of the non-recursive formula, these are the values from the probability table needed to implement Bayes formula, and then 5 left, 3 right roaring events indicate that I must build the conditional table like this with this code. I am just programming these expressions, and with a non-informative prior 0.5, then voila, application of Bayes formula with this code ends up telling me 0.0028 probability of being right, and of course 1 minus that 0.9972 probability of being left. So we checked that non-recursive and recursive give the same results as expected because we proved it, and importantly, the conditional independence assumption was valid in my simulation because, well, apart from this list of observations that I am not going to comment, in here the new observation, if it is left or right, just depends on the random number generator, and this probability, in this case it's always 0.8, so the random number below 0.8 does not depend on past values of observations. So the new observation is statistically independent, conditioned to real tiger, not changing side. So it's independent of past and future observations. So well, now we'll run the algorithm with these random observations instead of the list I used to check equivalence between recursive or not. And then I will make them a bit longer, say 20 roaring events and the prior. So if I run this simulation, well, here we have the observations. When I say 0 is left, when I say 1 it's right. And after, let's say, 9 events, says here, it's sure, except 1 in 5,000, that tiger is left. If I run the simulation again, the sequence of rows is different. Now it's sure in 7 observations, and I can do whatever simulations I wish. But okay, that's why I had in my code n simulations. So I will superimpose 40 simulation, let's say. So well, I'm not drawing the observations when having multiple simulations because, it's a bunch of left and right randomly arranged. But well, we see that basically after 12, all of them are basically sure that tiger is left. If real tiger were at the right hand side cage, then I get these simulations. Now they take like 16 observations to be sure what side the tiger is at, in the worst case, let's say. And if observations are noisier, I may take longer to be sure on where the tiger is hiding. Indeed, I will simulate 500 rowing events because I'm going to change the conditional table to this one. So, I am hearing at the wrong location 45% of the times. So if I simulate this, then in some cases not even 500 rowing observations are enough to be sure on what's happening. If I change to 1500, then we see that one unlucky zookeeper had to wait for 900 rowing events until being sure that tiger is at the right-hand side cage. I can repeat it again, and we see that, it seems that the worst case time we need to be sure on tiger location is sort of almost 900 samples. This is a basic fact, in recursive filtering. If your sensors are noisy, then you need more samples to be able to estimate with a given accuracy the internal state of your system. In this case, internal state is tiger location. It's the random variable which is not accessible to us. Of course, if measurements were having a very low noise, conditional probability table close to identity, then on the contrary, this will take just 1 or 2 observations to be sure on where tiger is. Here is the table, and here's the simulation. Well, it seems that unlucky guys needed 4 rowing events in order to be sure that tiger was at the right-hand side door. So, okay, you can just change the probabilities, the number of simulations, and whatever in order to extract your conclusions and to understand the behavior of this recursive state estimation that is the key ingredient to the, recursive Bayes filter. For the moment being, we end here. Thanks for watching.